So we are going to learn about the topic called transforms right now. And transform is basically used to convert a signal in one domain to another domain. So previously we have learned in various subjects about Laplace transform, we have learned about Fourier transform, and you have learned about Z transform. So what did each of these transforms do? Laplace transform, your x of t was converted to x of s. So the transformation took from time to s domain. Your Fourier transform, it converted a signal in time domain to frequency domain. So time to frequency. Your Z transform, it was normally applied for a discrete signal x of n, and it got transferred to S plane. So your discrete time got converted to S plane. So that is what these transforms are basically used for. Now for our particular concern, we have now why do we use these transforms? And that is an important thing. You have learned about transforms in various subjects, but why do we use these transforms? So there are different cases where you need the signals to be analyzed irrespective of time domain or the natural state of existence. For example, you're having an audio signal, and okay, fine. So when we consider an example, let's take an audio signal or a song for an example, and imagine it's of size 10 MB. And you somehow want to compress it to 5 MB, which means you have to discard of some information. Now, one way of discarding information would be to get away with the unwanted components. So let us assume we already know the fact that audible frequency range would be in the range of 20 Hertz to 20 kilohertz. Now it's not possible for all of us to hear all the sounds in this span of frequency, but let us assume that it is existing, or a song has frequency components in this particular range. Now to reduce all these frequency components, one good option would be to filter it to the range of probably 1 kilohertz to 10 kilohertz. So just imagine a span of signal that is existing from 2 Hertz to 20 kilohertz, and you want this new set to be generated from 1 kilohertz to 10 kilohertz. You need only this much. So which means you would have learned about different kinds of filters. So you have an original audio file which is in this span of frequency that was previously mentioned, and you pass it through a filter. So you have learned about band pass filters, band stop, high pass, low pass. So the filter suitable here would be a band pass filter, and filter designed for probably this is a theoretical concept. So 1 kilohertz to 10 kilohertz, you have a band pass filter. You filter that and you get the modified or filtered audio signal. So now what would happen? Your signal now is now compressed in terms of, or you have got rid of all the frequency components that are apart from in the span of 1 kilohertz to 10 kilohertz. So naturally major information of your signal will be lost by then, and now your song can be compressed. Now what we had initially was a signal in the time domain. So normally your songs, like as you already know, it will be starting at a set time like this, maybe up to 0005 minutes and 30 seconds. So time is not getting affected. It's the same time span, but we are getting rid of these many frequency components. So you can compress a song like that, and for since nothing has been changed in the time domain, we need to analyze signal in the frequency domain. So what we need to transfer the signal from the time domain to frequency domain, and you can basically know the application of a transform in scenario like this. So that was my point, and I just wanted to give you an example of why transforms are being used. Now we are going to learn about different kinds of transforms that are under our particular concern. So we'll start off learning with three of them: Ctft, Dtft and Dft. We'll look into each of these transforms. So Ctft, as you might already know, it stands for continuous time Fourier transform. Dtft, it will be standing for discrete time Fourier transform, and Dft would be standing for discrete Fourier transform. Now if you ask me what each does, so we can narrate it like this. Ctft, by this you should be knowing the fact that x of t, it represents a continuous signal, and it will be converted into x of omega. Your Dtft will be x of n, the discrete time signal, which will be converted to x of omega, and your Dft will be x of n, which will be converted to x of k. So we are taking a look at what of these signals are. So we had x of t, x of n, x of omega and x of k. So like x of t is a continuous time signal, x of n is the discrete time signal, x of omega is the continuous frequency signal, and x of k is the discrete frequency signal. So typically, like if we have to take a look at it, okay, so we start off with Ctft, and Ctft, as we already know, it converts x of t to x of omega. Dtft, it converts x of n to x of omega, and Dft, it converts x of n to x of k. Now let's take a look at what each of these signals are doing. So x of t, as you already know, it is continuous and continuous in nature, and x of omega will also be continuous in its signal form. X of n is discrete, meanwhile x of omega is also continuous, and x of n is discrete, x of k is discrete. Now Dft is a transform that is going to be majorly used in DSP applications, because we need discrete signals for the processing, and the output mostly generated will also be in discrete form. And hence x of n and x of k should be in discrete form, which is why Dft is the most preferred of all the transforms in DSP applications. So the focus will be on applying Dft and learning more about it. So but in the meanwhile, Ctft is something that you are already familiar with while you have done your signals and systems. So you would remember the formula of this sort: x of omega is equal to minus infinity to infinity x of t e raised to minus j omega t dt. You would have remembered this particular formula. When you apply this concept to your Dtft, the discrete time Fourier transform signals, your output is again x of omega, but here just because of the fact that it is a discrete signal, the integral, it changes to summation, and it becomes minus n equal to minus infinity to infinity x of n e raised to minus j omega n. And these are the two different formulas that we need to understand about Ctft and Dtft, and these two should be clear to you because of your prior knowledge in signals and systems. So this can be learned and applied in case if your problems come for your exams. And in the meanwhile, we'll have to go for a deeper analysis of DFT, or rather, how does this x of omega, which is continuous, gets discretized in the form of x of k. We have to understand that. So x of omega, like I mentioned before, it is a continuous signal, but x of omega is having another one property, that it is periodic over the interval 2 pi, which means if this is an interval 2 pi and this is an interval 4 pi, this is 2 pi and this is 4 pi, thereby making the interval same, the output or the signal in this duration will be periodic as well as continuous. Continuous implying it exists from minus infinity to infinity, so there is no doubt about that. But there is another property called periodicity, basically implying the fact that it will be periodic over the interval 2 pi, which means it will be repeating over the interval 2 pi, and hence you don't have to consider this entire span of this signal. So assuming that I'm considering that 2 pi span, and if I divide this into n samples, so this is a signal in omega domain and this is x of omega, and I'm trying to convert this into discrete signals, and I have n samples here. So the span between each of these interval between the two signals will be 2 pi by n. And assuming we have a variable k to represent the position of the sample, so like 0, 1, 2, 3, 4, we have a variable k. Okay, now when we were converting our discrete time signal, or creating a discrete time signal from your continuous signal, time signal, we had implemented a formula like this: x of n is equal to x of t, where t is equal to n capital T. So this was the variable representing the position of the sample, and this was the sampling interval as shown in the previous video. This was the concept of discretizing a signal. So in that, applying the similar concept, x of k will be equal to the sampled version of x of omega, where omega is equal to, we need to substitute these two variables over here. We need a variable to represent the position, which is already k, as already mentioned in the previous place, and in the sampling interval in this case is 2 pi by n, which was. So once we apply this concept into the DTFT formula, so we had already written a formula for DTFT where x of omega is equal to summation n equal to minus infinity to infinity x of n e raised to minus j omega n. Your formula for DFT can be found out using applying this particular concept. So we are going to get x of k, which is a discretized version of x of omega, and this structure follows summation n equal to minus infinity to infinity. X of n remains as such because it is the one that is being converted, and instead of omega we substitute it with 2 pi k by n into small n as existing in the previous formula. We are substituting for omega with this 2 pi by n into k, and hence the final formula becomes summation n equal to minus infinity to infinity x of n e raised to minus j 2 pi n k by capital N. So this is a formula for DFT. So we looked into three kinds of transforms right now. We looked into continuous time Fourier transform. We wrote the formula for that. We looked into discrete time Fourier transform, and we looked into DFT. So as I mentioned before, for DSP applications, implementing questions with DFT would be the top priority. So that is a problem that we are going to look into, and we'll do the problem in the next video.